of the concepts we've studied throughout the course. Don't take a review lightly. A review is a very important part of the learning experience. A person can usually comprehend a concept better the second time because he has a better understanding of the subject as a whole. In addition, the review will give you an overall view of the study of physics. Science, in its simplest terms, deals with interactions. In physics, we examine the interactions between matter and energy, sometimes defined more simply as the science of matter in motion. Science deals with the processes, such as observation, by which information is collected and organized to make it more easily understood. Physics would be severely limited without experiments or controlled observations. The science of physics can be divided into several branches. That branch of physics dealing with motions and forces acting on material objects is known as mechanics. Mechanics is usually divided into kinetics, dynamics, and statics. Kinetics is the study of forces and of torques upon the motions of material bodies. The forces that cause changes in motion involve the area of dynamics. On the other hand, physicists who study bodies at rest and forces that keep those bodies at rest are occupied with the subject of statics. Another branch of physics is called kinematics. Kinematics is the mathematical description of motion without regard to forces or bodies of matter. A body can have two distinct types of motion, translation and rotation. During translation, an object's center of gravity moves, displacing the object from one position to another. Rotation is motion around a fixed axis. To assess the motion of a body, its speed or velocity must be determined. Both speed and velocity are found by dividing distance by time. Speed is a scalar quantity, and velocity a vector quantity. When the speed or velocity of an object changes during a certain period of time, its motion accelerates. Acceleration is the rate at which velocity changes. The change in velocity divided by the change in time. Acceleration is a vector quantity. When physicists examine the motion of objects, they also desire to research the causes of that motion. One natural cause of acceleration is gravity. Acceleration due to gravity, g, is constant at any one point on Earth. Its value is usually given as 9.81 meters per second squared to 3 significant digits. However, the value for the acceleration due to gravity is not the same everywhere over Earth. It's slightly less at the equator than at the poles due to the bulge of Earth. Increasing the distance of a body from Earth's center decreases the effect of gravity upon that body. Therefore, as a body rises above the surface of Earth, the acceleration due to gravity decreases with the square of the distance. You may recall equations used to describe motion. 4 quantities used in the equations are distance, s, average velocity, v bar, final velocity, v sub f, and acceleration, a. Given any 2 of the 4 quantities, the others can be found. Straight line motion is easy to describe mathematically, but many bodies do not follow a straight line. For example, Galileo showed that a projectile follows a parabolic path. A projectile is any object that does not propel itself after being launched. Galileo also showed that projectiles have both vertical and horizontal motion, and that the vertical and horizontal components of velocity are independent. The horizontal component of a projectile at the instant of launch can be determined by multiplying the initial velocity, v, by the cosine of the angle of launch measured from the horizontal. Acceleration due to gravity does not act on the horizontal component. For that reason, the horizontal component of velocity is constant throughout the flight of the projectile, provided air resistance is not considered. The vertical component at the time of launch can be calculated by multiplying the initial velocity by sine theta. Acceleration due to gravity does act on the vertical component. When a projectile achieves its greatest vertical distance, we say that it has reached maximum height. The greatest maximum height reached by any projectile occurs when the projectile is launched straight up, that is, at an angle of 90 degrees. The smallest maximum height, 0, occurs when the projectile is launched horizontally, that is, 0 degrees. The horizontal distance from the launching point to the point of impact is the projectile's range. A projectile has its greatest range when launched at an angle of 45 degrees. Elapsed time from the moment a projectile is fired to the instant of its impact is called the time of flight. Time of flight is longest when a projectile is fired straight up. When a fixed body, such as a guitar string, is set into motion, it experiences periodic vibrations, up and down or back and forth, called simple harmonic motion. The force that displaces the body is countered by a force acting to restore the body to its original position. The restoring force acting upon the body is proportional to the body's displacement from the center of its path. This is the fundamental property of simple harmonic motion. The motion of a pendulum approximates simple harmonic motion. Simple harmonic motion can be analyzed in terms of circular motion, such as that of a pendulum. A pendulum slows down as it moves away from the center of its swing and speeds up as it returns to the center. The time required for a vibrating body to move from the point of maximum displacement on one side to the point of maximum displacement on the other side and back again to the first point of maximum displacement is known as its period. Therefore, a period is one complete vibration. The number of vibrations, or periods, per second is called the frequency of a simple harmonic motion and is expressed as the reciprocal of the period. Clocks keep time based upon simple harmonic motion. The simple harmonic motion of a pendulum, the simple harmonic motion of a hairspring winding and unwinding, or the vibrations of a quartz crystal. Capable of producing motion or a change in motion of a material body can be called a force. The amount of force that causes 1 kilogram of mass to accelerate at 1 meter per second squared has been defined as a Newton in the SI system of units. The dyne, a smaller unit of force in the SI system, causes 1 gram of mass to accelerate at 1 centimeter per second squared. Any force that causes the deformation of a solid is known as a stress. The 4 most common stresses are stretching, bending, compressing, and twisting. A body that resumes its original size and shape after being distorted by a stress is an elastic solid. A body that does not resume its original shape is an inelastic or plastic solid. When an elastic solid undergoes as much stress that it will no longer return to its original form, it has reached its elastic limit. While experimenting with stress and its distorting effects on bodies, Robert Hooke discovered that the amount a body is deformed is directly proportional to the force causing the deformation. Physicists now refer to this phenomenon as Hooke's law. As you know, there are two types of motion: translation and rotation. Torque, the force that causes rotation, is equal to the force multiplied by the length of the lever arm. Lever arm distance is defined as the perpendicular distance from the force vector to the pivot point. The perpendicular distance is the shortest distance between the point of rotation and the line along which the force acts. When a body is at rest or has uniform motion, we say that it has equilibrium. Whenever the center of gravity of a body remains at rest or stays in straight line motion at a constant speed, that body has translational equilibrium. The resultant of all concurrent forces acting upon a body having translational equilibrium is zero. If a body is not spinning, or if it spins at a constant rate, then that body has rotational equilibrium. If a body has rotational equilibrium, then the sum of the positive, counterclockwise torques equals the sum of the negative, clockwise torques. Though there are only two types of motion, there are also many combinations of these two types of motion. All motions can be represented by some combination of translations and rotations. If a body is not accelerating and its rotation is uniform, then it has both translational and rotational equilibrium. Sir Isaac Newton recognized that the motion of a body follows three laws. The first law of motion, also known as the law of inertia, states that every body continues in its state of equilibrium unless it is compelled to change that state by forces impressed upon it. Inertia is the tendency of matter to remain in its present state. Force is required to overcome the inertia of a body of matter. In mathematic symbols, the first law states that if the force on a body is zero, then the velocity of the body will remain constant. The second law of motion concerns bodies in motion and defines the acceleration of a body in terms of force and mass rather than velocity and time. According to the second law of motion, the acceleration of a body is directly proportional to the resultant force acting on the body and inversely proportional to the mass of the body. The acceleration of a body is always in the direction of the resultant force. The second law of motion is also known as the force equation. It can be rearranged to state that force is proportional to the product of mass and acceleration. The first law of motion is a special case of the second law, in which the force is zero. Thus, the velocity of the mass will remain constant, since it will not be accelerated. The third law of motion states that when any two bodies interact, the force exerted by the first body on the second is equal and opposite to the force exerted by the second body on the first. The third law of motion is also known as the law of action-reaction. The propulsion of a rocket into space is an illustration of the law of action-reaction. At present, powered flight in the frictionless void of space can only be accomplished by the action-reaction principle. Mass must be discarded in one direction to send the rocket in the other. A body forced into motion has momentum. Momentum can be calculated by multiplying the mass of a body times its velocity. The force that gives momentum to a body is known as impulse. Impulse is the product of force and time. Time refers to the amount of time that the impulse force is in contact with the body to which it imparts momentum. Since the total amount of energy of the impulse force is transferred to the body having momentum, impulse and momentum are equivalent quantities. That the total momentum before an impact equals the total momentum after the impact is the law of conservation of momentum. Thus, conservation of momentum is a direct consequence of the third law of motion. From these three basic laws of motion, other laws of motion have been described. For example, Johannes Kepler described the laws of planetary motion by observing the movements of the planets. His first law of planetary motion states that each planet moves about the sun in an elliptical orbit, with the sun as one focus of the ellipse. Kepler discovered the second law of planetary motion when he noticed that a straight line joining a planet with the sun sweeps out equal areas in equal intervals of time. Kepler's calculation